Alright, so let us start off with our section today. Please come. Alright, so we are in the process of discussing digital signatures, if you remember. And the basic process was that in this segment, we are trying to find out that the individual user will have a certain signature based on the message that it is going to send. And that signature needs to be tested at the receiver using some algorithms, which primarily what we have discussed so far, we can observe that the same kind of algorithm we have discussed in the crypto system as well. So the similar kind of algorithm with certain steps, different steps are to be adopted in finding the two elements. One is called as the signing part. This is basically the encryption that we have done in our crypto system. And there is something called as verify, which happens to be the decryption that we were calling it at some point. So, but the important aspect over here is that whatever happens, we are discussing only to find out or to verify whether the signature is correct or not. Not the message is important over here. It's only the discussion on the signature. So based on that, we have found out that ideally there are few schemes which are readily available, in which we had already discussed about RSA and LGAML. So if you remember, if I happens to show you that, so let me just show you the diagram itself. So this was RSA, which is primarily based on the same technique as we have done before itself. But the only change is over here, you can see like why it is different. Like in this case, you can observe there is a signature which comes in over here, and there's a message which is separate. And this signature goes into the receiver, where again a similar decryption kind of a process, or we call it the verifying process, happens based on the private key and the public key of Alice. And based on that, we verify whether the signature is correct or not. And if it is okay, then we will consider that the user who has signed the document is perfect. We don't have any problem with it. But in the same manner, in this, one of the biggest drawback is that here we are sending a single signature based on the user. Instead of that, what LGAML suggested is that divide the signature into two halves. And that is where it becomes different to that of the RSA. Here you can observe there are two halves of the signature, S1 and S2. And primarily S2 will be again dependent on S1 and how it has been generated. So in a way, we are giving kind of an abstraction to the two signatures which are generated, and thus making sure that the encryption or the signature generation is much more secure. So in this, if we remember, we had discussed this on a PDF. So let me just show you that. So this was a PDF that, sorry, yeah. Alright, so this was a PDF that we were referring to in the previous day as well. So in that we had discussed about the LGAML scheme, and initially most of the things are same except that the signature part, where we are using S1 as one of the part of the signature is given by alpha to the power k. Alright, alpha to the power k mod of q, where alpha is the primitive root, k is a random number which lies between 1 to q minus 1, and q is the prime number. Very similar to the previous example, except the one small different step that is happening, and that is over here, where we have to calculate the multiplicative inverse of the value itself. So if you observe, this is k inverse we are generating. So we have not done in the previous case, although we have done in a way E multiplied by D. It was there in some other RSA, I think we have used that, where E and D were multiplicative inverse to each other. The same concept is applied over here, except that it's expressed in terms of K inverse. That's it, nothing else. And finally, we obtain S2 as well over here. So S1 and S2 becomes our signature. So at the output, this already we have done. In fact, last day itself we have done. So in that case, what we are observing that V1 must be equal to V2. And that in that note, we have also done one numerical in that what specific thing I told you, that given all the feature, what the main objective is to find out whether V1 is equal to V2. We are not bothered whether the output of V1 and V2 doesn't match to the message. By that, what I mean is, like in this case, the message I think was 11 or 4, something like that. Yeah, message was 14. So we are not bothered whether the message 14 which was sent at the transmitter remains as it is at the receiver. We are not bothered with that. Here M is actually not the message, it's the digest of it. But if you observe here at the end, what we are verifying is only the signature. And to verify that, we require that V1 needs to be equal to V2 based on the steps which are needs to be followed. So this is what we have discussed in last day's class on LGAML. So let us now quickly start with the next half, which is the SNOR digital signal scheme. This is also primarily similar. Same purpose is the same. You will also observe here also. We are going to generate two set of signatures in the same manner using some certain steps. But remember the important contribution of this algorithm, because the first line indicates it reduces the message dependent amount of computation required to signature. So compared to LGAML, we are using less number of, we are making sure that the signature is not dependent on the message. That's a very important step. Alright, so irrespective of the message, the signature can be verified and can be changed. So let's see about, so signature generation does not depend on message directly. Indirectly, though it might require, we'll see that. Alright, so let's see the process again. And in this process, few things needs to be understood very carefully. So please focus on it. Those who came late, please focus on it. We are starting new today. Two things to be important in this particular segment of SNOR digital signal. One is we are considering two random numbers P and Q. Unlike to the previous case where we are only having one prime number. But here, one very important factor is prime factor. Q is a prime factor of P1. Or P minus 1 rather. That is the only important thing. P and Q can't be any prime numbers. P and Q will have a relationship, and that relationship is given by P minus 1 mod of Q should be equals to 1. This should be considered while choosing P and Q. So given any prime numbers, you can take any large prime number, but they should be prime 1. Q should be prime factor of P minus 1. So if you take the example that I've considered, 5 and 7 we have considered P equal to 7 and Q equals to 5, and this supports the claim, and hence we can say that 7 and 5 can be considered as the two prime numbers in this case. Just for a small example I'm talking about. So this prime factor was not there in the previous example. So this is one thing that you need to know. The others are almost the same. You can see that we are generating the public elements over here, as we have done for the last few classes for most of the algorithm. So P is the prime number, Q is known public numbers, A is such that a prime number. This is also A to the power Q mod of 1. So A is basically another public element. Based on this, we are generating a private key. So this is again something very interesting and a new thing that I want all of you to note down or remember it in that way. Up to this point, whenever we were generating the private key or the generation part, we never had used this particular formula. If you check here how we are generating it, V to equals to A to the power. A is the random number that we have generated over here. Alright, so A is the public key to the power minus S. Alright, this is something very different. This is not to the power minus 1. It's not the multiplicative inverse that we come across. This is like 5 to the power minus 3 mod of 7. Something like that maybe you can say. Now this is something different. 5 to the power minus 3. Okay, so we have only done with power which was, or the exponent part is positive. Or if it is minus 1, maximum we have done the multiplicative inverse. Alright. So in here, if it comes over here, please make a note of this. Okay, if at all numerical comes from this, as I said, very rarely we get a numerical over here because the steps are a bit lengthy. So please make a note of this. If you come across this kind of scenario in modular arithmetic, what we can write is, if it is A to the power minus S mod of P, this is nothing to do with the algorithm, it's just a modular arithmetic part. We can write this as B to the power S mod of P, B to the power S positive, considering A and B are multiplicative inverse. So please make a note of this. So A and B, if they are multiplicative inverse to each other, then we can represent A to the power minus S mod of P to be equivalent to b to the power s mod of t. Now, if it is b to the power s, we don't have any problem. Because exponent part, if it is positive, we know how to compute. So this part is what? This formula is relatively, the property is unknown to us, so please make a note. If at all it comes in, if this is negative, because this is a generic formula, whatever you are generating s, it will come as minus s. As I have given an example, 5 to the power minus 3. Now, how will you compute minus 3? So that's why this is the logic. If you are equating this, it should be 6 maybe. Say 6 whole to the power 3 or 6 to the power 3 mod of such. Considering that 5 and 6 are multiplicative inverse to each other. If at all 6 is multiplicative inverse of 5, that we can calculate separately. Right, so this is about the V part. So using the private key, we are generating V, alright, and we are calling this as the public key. So using the private key, we are generating the public key. Remember, we have S as the random number and we are also generating V. So S and V, you can see here, using the private key S and the public key V, we are now generating the signature. Now let's see about the signature. Right? So now in the signature again, we are generating some kind of a, like we are assuming some random number R, which falls within this category, which has been there for almost, I think, all the equations for that matter. So there is a range given 0 to Q, alright, and you are generating what is called as X. Now the interesting part is, as I have told already, that for case of the Schnorr digital algorithm, we don't have the dependency of the message. So here if you observe, X is generated by the public element, by the random number R and the prime factor Q. So there is nothing as message over here. But this X will be utilized over here to generate the signature. You see here E is the signature. E is the first part of the signature. Remember, we are discussing, this is post Elgamal. So this is nothing but little bit an advancement to that of Elgamal. In Elgamal also we had two sets, S1 and S2. Here they are represented as E and Y. So if you say S1, this is equivalent, you can say, to E, and the S2 is almost equivalent to Y. So the same two parts of the signature is there, and that helps in reducing the improving the security of the signature, because we are not sending the whole signature all the go like in RSA it was doing. So compared to RSA, Elgamal is improved. Compared to Elgamal, this is more improved because here the message dependency is reduced. So you can see the formulation, and over here another important term, concatenate. This is the only algorithm where the concatenation happens with the message digest. So the hash and the X are concatenated over here. C is underlining the process, concatenate. Okay, because based on this only you will be able to identify the algorithm. Otherwise, it will be very difficult to identify. Most of the algorithms are very similar. We do the signing, we do the verification, we generate the public key, we generate the private key, we use those private and public key in the receiver. Very similar structure, except for a few keywords which will give you an idea which algorithm we are going to use. For example, in RSA, the keyword is the signature is only one. If you come across any question where the signature is only one, it's RSA algorithm that you have to explain. If you come across a scenario where the two sets of signatures have been defined, it can be anything for that matter. It can be anything. But suppose you don't have the concatenation like it's over here, then you can say that's an Elgamal scenario. If there is a concatenation word or concatenation that needs to be done with the hash, we can definitely say that's a Schnorr digital signature. You will soon find the last algorithm, the DSS and the elliptical, will also have certain specific properties, based on which you can identify which algorithm we are going to use. Correct? So this is about the generation part. So E and Y are my two keys which are there. And naturally, based on that, we will also have the verification stage, like in the previous case also. Equation just changes a bit. So you can see the equation has changes a bit. And finally, what we are checking is whether the concatenated message hash function is equal in both the cases altogether. As you can see, I have not given any examples over here, because as I said, the examples are not that important. The methods are important over here for the time being. So please focus on the method, and if it is asked, explain them with proper examples. Just take some random values and just check it. P and Q, how the conditions can be and all. Alright. So this is a scenario where we are discussing about the three sets of algorithm. We started with RSA, we improved it to LGAML, then from LGAML we are improving it over here for this non-digital system algorithm. Correct? Correct? Methods wise, I don't think there is much of a problem with all of you. There are processes generate the global element or the public element, generate the private element. In some cases, the private element is used to generate the random key once again. Then we'll have a signing process where there will be the signatures which will be generated. Those signatures will be passed on to the receiver, and there will be a verification process where those signatures, you can see over here, the signatures of Y and E has been used over here to generate X prime. That's it. All right. So that's how the verification done. And in general, the diagram, as I said, it should be compared with the existing value and comparison. If it matches, we will say the signature matches. Same concept here. No check of the message. We are not bothered with the message over here. We are just checking whether E and Y are correct or not. And to check that, we have to find out that whether this equation holds true. That this is holding true. That's it. Okay. Keeping this in mind, let's take the last two, which are relatively newer technique, I would say, and the one that is we call as the digital signature standard or a DSA, which happens to be again very similar to doing a logarithmic process. As we know, the discrete logarithm, it's again a trapdoor function kind of, like reverse process is very difficult. That's why DSS was introduced in 1991 almost. But again, it got discarded after a certain period. But for the time being, let us discuss also the process of it, because it also involves very similar to the other algorithms once again, except for certain specific finite length of bits. For example, you can see prime number over here. Okay. Again, the prime number, same prime P, Q, we are generating same here also. Prime number, where prime number should be within this range, where this L indicates a specific range of 512 to 1024. So suppose in your question somewhere it comes in that the generation of the algorithm works on specific length of message bits or specific length of data bits, then you will soon understand that that's basically DSS algorithm that we are talking. Directly it might not be mentioned, explain about DSS algorithm, but from these key points you need to identify which algorithm we are going to use. So here if you observe, L is a multiple of 64, very similar to what we have done for the SHA 512 algorithm, if you remember, similar kind of structure. So P is generated by this, same way Q can be generated. Here you can see Q is a specific bit of 160 bit length. So the lengths are fixed. Got it? So that's what Q is, and it is called as prime divisor of P minus 1. That's one thing. And also we have another element which is G. Just like we had a primitive root in some cases, here it was termed as G, which follows a certain equation which is given here. H to the power P minus 1 divided by Q mod of P. And the conditions are also in front of it. So basically again, we are generating some global elements. Using these global elements, we are going to generate the private element and the public key, public key and the private key. So let's see of the private key, very simple. X is a private key, which is a random number lying between 0 to Q. Same thing. Previous also we have done multiple times. And the public key will be generated G to the power X, where G is here. G to the power X mod of P. You can imagine, let's see the equations. They are very similar. There is not much of difference of it. Only the point is how you are generating that initial part. That's where the tweak is. In some cases, it is prime factor they are considering. In some cases, they are using prime divisor they are considering. In some cases, they are using primitive roots. In some cases, they are using only prime number. So that's how it's like, depend on the researcher, how they have come across the algorithm, the assumption changed. But the methods are same. Alright, so we have X and Y. So based on X and Y, the signing process and the verification process is given here, which I think you can manage on your own whenever I'll upload the document over there. So you have the R and S. So R and S is signified to something like R can be equivalent to S1 or can be equivalent to E in the previous example, and S is kind of equivalent to S2, maybe it is equivalent to Y. So same thing. So with respect to two sets of signature, you cannot differentiate much. But if it is with respect to a fixed length of sequence that we are considering, only DSS has that feature. So you have to identify the algorithm based on that. Okay? Again, the signing process and the verification process, you can see that finally what we are achieving is check V is equal to R prime or not. So what is R? R prime, and it's given over here actually at the end. So S prime, R prime, M prime, these are all my received data, received message, received key, received signature. R and S are the signatures actually. And based on that, we are going on through this process, which I think is not to explain much. It's just some equations where you have to split in and you get the result. You can see HM, this is the hash function, the received hash function with respect to multiply by W. Where is W? W comes in over here because it's kind of an iterative process that we are going through. And finally, we are receiving V over here and we are comparing again the V with respect to R prime. Okay, so that's how about DSS. Simple as that. The steps is what you have to look into, specifically the last equations and the verifying process. Okay, if it is asked to you, you have to explain this properly. No numericals, nothing will come from this segment. Simple as that. The last but not the least is what we call as the elliptical curve signature. Again, this is a process which I think many of you might be already aware of. Elliptical curve arithmetic, we all know. Using the same thing, we have done elliptical curve, the curve system, the crypto system also, ECC we have done. The same application is over here again using certain rules. The rules are very simple. The rules are here one keyword that makes it different to that of the other things. Wherever you will find the word extracting from the information or some graph, like here I have underlined. Okay, we have underlined over here because this is the only algorithm that we are starting over here where there will be data which will be extracted from an elliptical curve. Until and unless up to this point, whatever the algorithm, we were assuming the prime numbers, we were trying to figure out some relationship between them. Here is the first of the algorithm and in fact the last algorithm where we are going to take the data from an elliptical curve and we will fit in to find out what is the signature. Alright, so that is where it becomes different to that of the other because the calculation will be done with respect to elliptical curve arithmetic again. So the same thing. So you can observe here that there will be two functions F1 and F2 which will generate the two signatures S1 and S2. So let's see about the process once again. So first is Alice chooses a point EP A comma B. Hopefully all of you can understand this A comma B. This will be some point for the elliptical curve. I think we have discussed it in the class itself and even in CAT 2 we have given the questions on this, how to find out EP A comma B. The curve and the points, we know the process. So that's how, suppose that is given to us. So EP A comma B is given to us. Now the transmitter, which is Alice, chooses another prime number Q and a private key which is D. And you can also Q in this case doesn't have any relationship as such. In the previous two we had one as a prime factor, one was a prime divisor. Here nothing is there. Any Q can be possible. So now we have the element EP comma E1 like some point over here. No, Alice chooses a curve, so we have to choose any point on it. So that is represented by E1. See the nomenclature how it is done. E1 dot comma A. Like this means a point on the curve. This dotted means A E1 comma X no Y. Any point on the curve can be chosen as this E1. And based on that, we can also calculate what is E2 and that is given by D multiplied by E1. Now for that, for your own convenience, I have mentioned it also in the right. Previously, we know R is equal to P plus Q or how to calculate 2P, 3P like that, the same process to be applied. Here D is a constant, some integer value, E is a point, suppose P given. So suppose you have E1 which is X comma Y and suppose I consider this as capital E and suppose my D is given by maybe 2, suppose, just consider 2. So basically what we are trying to find out E2 equal to 2 of E. Now we know the process of finding out the equation, right? We know the process, right? 2P, the process, what is adopted? The same thing needs to be done over here. And we find out what is E. So we now know E1 which we have chosen from the graph and E2 with respect to the private key D we are generating over here, E1 and E2. Now based on that, you can observe the public elements I have mentioned over here. A, P is known, P, Q are known, okay, and E1 and E2 are also known. These are my public keys. All they are public elements. This is shared to everyone. Now what happens again, we know the two processes. One is signing and the other one is verifying. So the signing process involves again choosing some secret number. See, the term changes. Up to this point we are discussing it about a random number. We were choosing a secret key. Here in this algorithm it has been mentioned as secret number. That's it. And that R belongs to some condition again given within a range of the prime number itself. And we generate, this is where it differs. It generates a third point using this formula. Pu comma V is the third point which is given by R multiplied by E1 comma X comma Y, suppose. And that calculation is again same as that of calculating 2P, 3P, 4P, whatever you call it. Right? Now the advantage of it is that see the number of steps it reduces. This U that you are looking at, the first part of the PUV, the first coordinate of PUV to be calculating for S1. So see the S1. This U comes in from the first coordinate. Can everyone follow this? This is the unique step over here. Based on the 2 points, we are generating a third point. Okay? And the third point is represented as C, U, comma V. U, comma V is also some coordinates. The first part of it is used over here to generate S1. So again, the logic is very simple. We are going to generate S1 and S2. But how we are going to generate? In the previous cases, we were generating using alpha. In some cases, we are using the primitive root to calculate. In some cases, we are using A to the power something. A was a random number. Here in the same manner, instead of A, we are taking the first part because it is the coordinated system is elliptical curve. So you are taking the first element, first part of the coordinate. And hence we are calculating S1. And similarly, we are also using the formula over here. We are calculating S2. And if you check here, S1 and rather S2 is also dependent on what the S1 is. So S2 is dependent on the previous key, which is S1. You have the digest or the method hash function HM, which is given over here. Digest over here HM, and we have the private key of D, which we have chosen in the initial case. So all this calculation leads up to S1 and S2. That is it. All the calculation needs to be done with respect to elliptical curve. That's the only part. Okay. And finally, the verification does over here. It's just the reverse of it. We generate some intermediate values A and B using some techniques, the way it is mentioned, S1 inverse, S1, S2 inverse. You can check over here. Okay. The interesting part is after that you are getting another value T x comma y. Now T of x comma y is dependent on A. A is over here. And B, which is over here. And see over here. See, this is the first point that we have chosen. First point. And this is my second point. So E1 and E2 we have already chosen in the first step itself. So E1 and E2 have been considered. Based on that, whatever you are getting as T x comma y, the first coordinate x, should be equal to S1. That's the logic. The first coordinate of the intermediate, the final value T x comma y, the x should be equivalent to S1. And if it is matching, we will say yes, it is okay. Because if S1 is correct, S2 definitely will be correct because S2 directly is dependent on S1. Alright, so that's why we can only omit, we can only choose only like one step to verify the signature compared to the other cases where we are checking for more than one step for that matter. So all this algorithm, what it indicates is that the logic behind is that we will send the message along with the signature. Now how this signature needs to be generated is what the algorithms are suggesting us. And based on those algorithms, we are trying to verify the signature alone at the receiver using the decryption or the verification technique. So I would request all of you to please go through all these 5-6 algorithms that is there for digital signatures. And remember the keywords that I have considered that, like again, I'll repeat once again, for RSA, we are only having one set of signature. For LGAML, we will first, for the time being, we will first discuss about 2 set of signatures for that matter. Okay, we were doing 2 set. Then third, the unique feature for the Snort digital system was that in that case, we are using some prime factors and we were making sure the signature is not dependent on the message. Okay, and we were doing some kind of a concatenation some places. All right, then we were doing the DSS. DSS, I think we did the concatenation in fact. And then finally we receive the elliptical curve where the arithmetic is done with respect to extracting data from the elliptical curve itself, and we are feeding in for the generation of the signals. So these are some of the key features which will give you a trigger point that what example or which algorithm you are supposed to follow. Right? So that's all for the signature part. So let me go back to the presentation because we have only few things are left. So these already have uploaded in fact in the course page, so you can just go through. There are some examples over here as well, but as I said, the examples are not for the initial part it's okay, but for elliptical curve and all there is no example needed. Only the methods are fine. So this is DSS already explained with the diagrams and all. Some examples are here for your clarification. If you can just go through the method, you can just see and substitute this data and you will get the answer. I don't think it is required to explain. All the equations are the same, processes are the same. Just go through it, you will be able to find out. Only remember that V calculation, a to the power minus s mod k, that is a separate unique thing that needs to be done. So this is some of the comparison of the algorithm. You can see DSS versus RSA. So computation of DSS is faster than computation of RSA when using the same P, so the same prime number, it is much easier. And also you can observe that at the end we are only verifying only one signature and that is enough. That's another way. And the number of steps also is comparatively low. DSS versus LGAML. DSS signatures are smaller than LGAML signature because Q is smaller than P. That's another advantage of using DSS. So based on the requirement, we go on doing the process. There are ways of discussing even further, like each of these algorithms will have certain degree of protection against the attacks that we have discussed. So that is I'm excluding for the time being, not needed for as such. Each of them will have certain degree of vulnerability with the attacks. So that's what. Now elliptical curve, this is what we have discussed already. So the last of the portion that we are left with over here, in this case, at least we'll start a bit today, and that is the key management and distribution. I think this again, as I said, if you can remember these diagrams once again, I just thought of keeping this diagram once again. Hopefully this will refresh your mind. And if you see the marking also, this means that I have done it in the class itself previously. So key distribution center is the process in which we are trying to communicate with one transmitter to receiver, hopefully with all the due signature, hashing and all other stuffs are done. Now we want to communicate with the receiver. How we are going to do it? We are going to do it only by help of some kind of a KDC, which is a key distribution center. Any algorithm which doesn't use the KDC, this we have done in before CAT itself. Any algorithm that you suggest that we doesn't use a middleman, remember? The middle KDC, the Diffie-Hellman, the LGAML key exchange, the key exchange strategies were adopted for that. For that discussion itself, we had done all this. So KDC is a standard process in which the client and the server will talk among themselves, and there will be some kind of a session key which will be initiated by the KDC. Based on that, the transmitter and receiver will speak among themselves or transmit the data. Alright, so this we already have done. I think these diagrams will be familiar to all of you, but I've still kept it over here so that it recollects and refreshes your mind. So if you observe that example, MSC, I told you in wireless communication when we were talking about, we were using some kind of a central server which will connect to all the users using the BTSs and all. So that's example given here. But so that's why we are not focusing on that. What we are focusing on is the new strategy, which is fairly new, and the protocol that is called as the Needham-Schroeder protocol. So let me just give you that briefing as well. Process is the same, except that the lines, if you can read on your own and you can understand that how it to be done. The first thing is that we have Alice as the transmitter and Bob as the receiver. Alice sends a message to KDC with her random key, her identity and Bob's identity. So the transmitter is sending an information about its own identity and the receiver's identity. Very similar, you can compare in that way whenever we are trying to make a call. We are dialing a number, right? So that number will indicate some kind of a link up to the device that we are supposed to call. And in that way, the BTS in between, which is basically the KDC, will check both the user at the transmitter and the receiver, are they authenticated user or not. Do they deserve a phone call to be established between them? Same thing is happening over here. Alice is sending, I am sending a request, I am dialing a number. The number along with my own information and the receiver's information will go to the central server, which is the KDC. So here the KDC lies here. So Alice is sending the information and this RA is indicating a random indicator to the user. And that's the second one is the KDC replies a message to Alice with Alice's random key and Bob's identity, the receiver's identity and a session key. So the session key is what? Based on that only we will try to, it's like a timestamp. There will be a timestamp with the session key. Like at what time you are supposed to make the request, by what time you are supposed to get in the channel. Because remember, all this will happen mostly either in wired or wireless. Now if you take a wireless, and if I consider only for the mobile, which is more easier for you to understand, in all the cases you need a vacant channel. You need a bandwidth over which you are going to communicate. So this session key or the timestamp will indicate that. Based on that only you are trying to communicate, because if the channel needs to be free, otherwise how will you connect? Right? So that's where the session key becomes important, and an encrypted ticket to Bob. Alright, so you can see here at 2, the direction of the action you can see. This is the direction, first direction. Then it goes like this. Then the third one again it goes like this. So third one is Alice sends Bob the ticket. Alice sends the ticket to Bob. Then Bob sends a challenge to Alice. Challenge means kind of a acceptance that yes, I am free, you can send me the data, or I am free, I am able to receive a call. If you consider a phone call, you are calling your parents. Your parents is the intended target, or the Bob for that matter. If suppose he or she is talking to someone else, naturally you will be forced to say that the other intended user is busy, because the channel has been utilized or being utilized now. Please call after some time. Same thing is over here. Here the intended user will try to, in a proper manner, like in a proper sense, the receiver will send the acknowledge that yes, this is, I am free, you have reached the right person, please do send me the data. So that is basically is given through an encrypted session key. And finally, you can observe that fifth one, Alice responds to Bob's challenge by sending the RP-1 instead of RB. So he encrypts the data once again and he sends the information to the user. So this particular technique that you are looking at here, the user is sending the process is involving using the KDC and using the session key as well as a ticket. Alright. The same thing, the same logic, it's very similar, is done in Otway and Rees protocol as well. See the diagram is very similar again. Alright. So here also the thing is, the difference is Alice sends a message to Bob with a common R, which is a public key you can say, and the identities of Alice and Bob, ticket for KDC. So that is one ticket which is sent from Alice's end. Remember in the previous case, the ticket was sent from KDC first time to Alice. That Alice has circulated to Bob once again. Here, the ticket is also sent. One ticket is sent from Alice's end. That includes Alice's random number RA, a copy of R, which is this, which has been given by the KDC itself and identifies Alice and Bob. Alright, so that whole thing is sent over here. Alright, second point is Bob creates same type of ticket. So it directly goes to Bob. Bob with his own RB, random number, both the tickets are sent to KDC. So one ticket is sent to KDC by Alice and the other ticket is sent from Bob to Alice. So both way it is transmitting. In the earlier case, it was only one way. Alice was sending, Bob was receiving. Bob was receiving it, but here Bob is also sending one of the ticket over here. KDC creates a message that has R, ticket for Alice and a ticket for Bob. So basically, KDC is the middle man. It is checking both the Alice's ticket which contains Bob's information and Bob's ticket which will contain Alice's information. And based on that, it will agree and will generate a session key. So you can observe the process is very similar to the previous one, except the protocol is little bit changed, little bit tweaked. Alright. So that's all about the second protocol, the Otway one. Alright. So, and the last one, again, I'll just start of it and you can do the rest of the calculation like the reading on your own, because I can understand it will become a little boring for that matter because it's a more of a theory as much. But this is the one which is the latest which is used right now. Alright, you can see the second point. The Kerberos is the built in all major operating system as that of Windows, Apple OS and the Linux as well. So this is ideally a process in which what happened is it's a three-way working. This client, the server and the KDC all together forms a single system. So that's basically the idea. And that if you observe the diagram at the top, it's a dog with three heads. And that has been given, the protocol was named after the character Kerberos from the Greek mythology, the ferocious three-headed guard dog of heads. So for that, this is the diagram of it. So I found out that this is pretty interesting in a way. But anyway, so how it works, the structure of it, okay? So let me just show you that what are the properties of it. One, see, they are very similar and very much common to all our practice. One is the user's password must never travel to the network. What are the policies of Kerberos? Then next is user's password never be stored in any form. I think these words are very common to all of you while you are downloading any app, while you are checking your internet or you are signing for some purpose and all. You will find all these are relevant for that matter. Alright. User's password should be never be stored in encrypted form even in the authentication server. Alright. So now this is the first time you will observe that this is the first time where an architecture will have two sets of servers. So let me just go directly there itself. So you can observe over here that the KDC, which was supposed to be only one set of server, now it has been divided into two half. One is called as authentication server and the other one is called ticket granting server. In KDC, the previous two protocols, there was nothing like that. It was only a KDC which was handling all the traffic. Here, ticket generating is separate and AS is separate. Why it has been made different? Because this is the only protocol where the user, if you consider the server over here or the client rather over here, like Alice over here, it will directly send the request to the authentication server to correct the scenario. So unlike the previous cases where it has to send to KDC, KDC will take the initiative of sending it to the authentication server somewhere remotely located. Here the user directly goes to the authentication server and that too sending using only a plain text. You'll see the next line, I think it's there. Alice sends a request to the authentication server in a plain text using her registered identity. This is the only protocol where the user directly sends a request to an authentication server. Authentication server, or normally the KDC will accept, KDC will decide the authentication process. Here, the user directly directs the authentication process. So that's how it is unique and why it is different. So next one is, you can see ticket granting service. So it issues a ticket for real server. You can see the TGS is for Bob. This is dedicated for the Bob server. Now we have there are two servers. You can see one is the KDC and this is the server which is Bob, which has a separate mind of its own. Alright, so the ticket granting service issues a ticket for the real server. This is where it's supposed to communicate. So in between this KDC, which has the authentication server and a ticket which will be generated, real server is where Bob provides the service to the user. So in a way you can say that there are two such of KDCs which might be there somewhere. One that takes care of the user Alice and its ticket service, and the other one is taking care of Bob and to initiate the call and the request to Bob. So let's see about the final conclusion over here. As you can see, the authentication server replies with an encrypted message with Alice's permanent symmetric key. The message has two session key. One part is session key and the other one is a ticket. Same thing like we have done. When the message arrives, Alice types the password which is issued by the client process to create the algorithm, the KAS, which is a symmetric key, and decrypt the message to extract the session key and ticket. So Alice will receive it from the authentication server itself. Alice sends three items to the ticket granting service. One, the name of the real server, the timestamp, that is the server, the session key, and as well as the message has to be the tickets received from the authentication server. So the authentication server sends it back to Alice. Alice will take that ticket. It will send the Bob's information, that ticket, and the timestamp at what session key we are supposed to get the idea. So you can see the fourth one, TGS. sends 2 tickets, each containing session key between Alice and Bob, and the ticket of Alice for Alice is encrypted with this one, and ticket of Bob is encrypted like this. So it is very similar to the Otway one. Both way we are sending. Alice sends the Bob ticket with a timestamp, and Bob confirms it by adding 1 to the timestamp, and it confirms that yes, I am the intended user, and try to communicate accordingly. So that's all with the Kerberos technique. I think I have gone a bit fast. The reason is that you can read it on your own and you can get an understanding of it. So there is not much discussion that needs to be done over here. Please go through the algorithm, because there again, only key management strategies, nothing more that will come except that the process involved. So please go through it and try to come up with an answer. Right? So let's stop at this point.